A snake travels as a single, unbroken line. It crosses the forest floor without feet to push off the ground or wings to generate lift, appearing to move by sheer will. This limbless design is a global success, supporting over 3,000 different species in environments ranging from dense jungles to open oceans. It is easy to assume the animal is simply sliding across the earth, shifting like a length of rope being pulled by an invisible force. That smooth glide is a disguise for a complex internal system. Beneath the skin, a specialized skeletal engine generates constant forward momentum. A snake's anatomy centers on hundreds of individual ribs, serving as the framework for a massive network of overlapping muscle groups. These muscles fire in a precise sequence, sending waves of energy traveling from head to tail in a continuous loop. Under a microscope, belly scales reveal a jagged directional texture. They catch against microscopic ground imperfections, creating a physical friction lock. As the muscle wave reaches these scales, it pushes down and back, creating a forward vector of force, driving the body forward. The snake operates as a self-contained biomechanical engine, generating its own propulsion through internal physics. This engine allows the snake to shift through different mechanical gears depending on the terrain. The primary gear is serpentine locomotion, where the body flexes into a series of S shapes. In this model, the outer curves of the S act as leverage points. The snake pushes its weight against rocks, twigs, or clumps of grass to propel itself through the environment. This system relies on solid obstacles for resistance. On the loose, shifting sand of a desert, there is nothing for those S-curves to push against. To solve this, certain species use sidewinding. They lift distinct sections of the body entirely off the ground, throwing themselves sideways in a series of continuous leaping loops. This technique provides vertical traction on unstable sand, while simultaneously reducing the amount of skin exposed to the searing surface heat. Sidewinding demonstrates how the snake's internal mechanics can be reconfigured to maintain speed in low-friction environments. Different physical constraints require different solutions. A wide lateral push is impossible inside a narrow tunnel or while climbing a vertical tree trunk. In these tight spaces, snakes use concertina movement. They anchor the tail end against the walls, expand the front of the body forward, and then anchor the head to pull the rear up behind it. Mechanical challenges also change with scale. For massive species like the python, the energy required for constant curving is often too high. These giants use rectilinear movement. They travel in a perfectly straight line by independently lifting and dragging sections of their belly skin forward, moving with the steady pace of a conveyor belt. From scaling vertical cliffs to dragging massive weight, the snake has evolved a specific mechanical gear for every terrain on the planet. When pushed to its limits, this biological engine produces explosive energy. The black mamba can reach speeds of 20 kilometers per hour, capable of outrunning a human over short distances. Yet speed is rarely the priority. Most snakes use their muscular control for silence, moving through their environment with zero vibration to avoid detection. This mechanical focus on stealth and avoidance is their primary defense. Rather than seeking confrontation, a snake uses its mobility to distance itself from potential threats before it is ever spotted. The creature is a specialized survival machine, representing millions of years of evolutionary engineering, refined for total terrain mastery. Scientists and engineers are now studying these exact muscle firing patterns to solve human transportation problems. They are designing robotic explorers based on the snake's anatomy. These machines are built to navigate the jagged rubble of disaster zones or the rocky surfaces of other planets, where wheels are useless. However, modern technology still struggles to match the energy economy and versatility found in the natural world. If we can eventually replicate these mechanics, our machines will be able to access the most unreachable corners of our solar system. A blueprint for navigating the most complex physical environments on Earth already exists, hidden in the anatomy of an animal with no legs.